My name is Grzegorz Filip, and I am a naval architecture and marine engineering graduate student. This summer, I had a chance to work with Professor Michael Bernitzes and Professor Gavin Mackey on a topic which focuses on computational fluid dynamics for simulation for submerged cylindrical bodies. I was also tasked with several side projects, which I will highlight throughout the presentation. Let me begin with a brief introduction of the project as a whole. Professor Michael Bernitzes leads the VIVACE group, or the Vortex-Induced Vibration Aquatic Clean Energy Group. This is an alternative energy project which aims to extract energy out of movements of water, such as currents and tides. A horizontal cylinder placed in water, perpendicular to the water flow, will shed vertices, and this shedding of vertices will result in net lift on the cylinder. VIVACE aims to extract this lift and convert it into electrical energy. This is a short video of one cylinder being tested at the Marine Hydrodynamics Laboratory. The flow in the channel is circulating clockwise. The flow is moving from left to right, and vertices are shed, and the cylinder begins to oscillate. It is connected to springs and an electrical generator to capture the electricity. Future large farms with hundreds, if not thousands, of cylinders are planned, as pictured here on the right, and that is where my summer project comes in. My research tasks included a CFD benchmark for various fixed cylinder configurations. I used Gambit, a software to produce numerical representations of the underwater cylinders. Then I looked into several commercial CFD codes. One of them was StarCCM+, the other was Fluent, and I also looked into an open source freeware known as OpenFOAM. My side project included a design for a multiple cylinder setup for a laboratory testing. I also carried out a conceptual study for river deployment of small modules for the VIVACE project. Finally, I looked into sizing of a new computational cluster for VIVACE to decrease the time necessary to solve CFD problems. And for my results, I started with Gambit to produce numerical representations of the underwater cylinders. I created setups for 1, 2, and 3 cylinders. In this picture here, we see 2 cylinders, which are separated by 8 diameters in the flow lie separation. The flow domain contains approximately 190,000 nodes. OpenFOAM, the freeware CFD code, was chosen as the primary simulation package due to its flexibility, as it stems from an open source design, as well as a large community of developers. OpenFOAM is also a freeware, as I said before, which makes it a much better choice for a research scenario. And this is a video of a result of an OpenFOAM simulation. Here we have 2 cylinders with the 8 diameter flow rise separation. The flow is coming in from left to right and is colored by velocity magnitude. As you can see, the blue areas are the slow areas, which are shed from the leading cylinder and affect the trailing cylinder. These slow areas decrease the inlet velocity for the trailing cylinder, which reduces the lift it creates, and hence it can produce less energy. This is a 3-cylinder setup where the cylinders are in a triangle and are separated by 8 diameters. Again, the flow domain has identical properties as before. This is Reynolds number of 10,000. The flow comes in from left to right. As you can see here, the leading cylinder has much lesser effect on the 2 aft cylinders, as all of the cylinders obtain relatively disturbance-free inlet flow. And as far as my side project, these are 2 designs, computer-aided designs for a 2 and 8 cylinder testing apparatus, which is to be installed at the Marine Hydrodynamics Laboratory. On the left, we have the 2-cylinder, and on the right, we have the 8-cylinder apparatus. It would be attached to a carriage inside of the tow tank at the facility. As far as the river deployment, a very simple concept was created where two inflatable pontoons are attached to the 8-cylinder module. The module is towed into the target site, and the pontoons are deflated and sunk to the bottom. Finally, a computational cluster was sized based on results of fluent benchmarks as well as a scale study which used a 90,000 node grid. The graph below shows the results of the study, where on the y-axis we have the computational time in hours, and on the x-axis we have the number of CPUs used. The problem took approximately 5 hours to complete with 1 CPU and under 1 hour with 8 CPUs. Further scale studies need to be carried out to account for the memory used and the computer architecture used. I would like to thank Professor Michael Bernitzes and Professor Kevin Mackey for allowing me to work on this project, as well as SURE for providing such a great experience this summer. I would certainly recommend it to anyone who would like to get hands-on experience in research. Thank you.